Well, hello friends. In this video, I will be discussing on the topic of thermodynamics as a resource theory. So we have discussed resource theory starting from the noisy operations, and we saw that we require free state and free operations to characterize resource theories. So in thermodynamics, we lay the free states as the Gibbs states associated with the bath. Here the system, the ancilla R is the bath. So Gibbs states are the zeroth state, and hence the bath is said to be present always in the maximally mixed state. Not maximally mixed state, the bath is said to be always present in the Gibbs state or the thermalized state. And the beta parameter that appears in this Gibbs state is what quantifies the temperature and serves us the purpose of the zeroth law. Now, what are the free operations? The free operations here are the unitary operations and partial tracing, similar to noisy operation, but in this case, these unitaries are energy preserving. So this commutation relation, we see that it is 0, that we see here in this commutation relation. This means that the unitaries are energy preserving and the total energy of the system remains constant, and that is what gives us the formulation of the first law. Now, once we have these two free states and free operation, we can ask that what are the thermal operations similar to noisy operations that we had before. So in this, thermal operations are of this form where a state goes to another state. They are related by particularly this identity that is boxed here, this one. So here we are using the free states and these are the free operations which are the unitaries. So now again we can see that this state S, the entropy of this state can only increase under such an operation, and hence the final entropy of the state can only increase. But it can increase up to a certain point, and the maximum entropy under the constraint of constant average temperature is that the maximum entropy is the maximum entropy the state that has maximum entropy under the constraint that the average energy is constant is the Gibbs state that we discussed in the previous video. So this means that the thermal operations takes the states closer to the Gibbs state, but it keeps the Gibbs state unchanged. So this is the formulation that states of a system equilibrate to the Gibbs state. Now, once we know that, we can ask that how the thermal operations, how they can be characterized. Similar to the fact that we saw noisy operations can be characterized by something called as majorization, we will see thermal operations are characterized by thermomajorization. So let's see. So in noisy operations case, we saw that such an operation means that the initial state majorizes the final state. And this was an order parameter. This introduced an order in the space of probability distributions. Now for this thermal operation, we say that if you take two states, so you have your initial state, final state, and they both are diagonalizable in the energy basis, in other sense they commute with the Hamiltonian, then such a transformation, there are theorems that discuss what happens if they don't commute. We need something called as dephasing operation, but that we will not go into detail. If they commute and the states are diagonalizable, then such a transformation is possible if the thermomajorization curve or the beta thermomajorization curve of the final state lies below the initial state. So we have to plot two curves, and which curve lie below or above that decides whether such thermal operations of this form will actually guarantee such a transition. So now let's see. So once we have given a state, how we can plot this thermomajorization curve. So given a state rho, we can diagonalize it in the energy basis. It will give us these eigenvalues, but these eigenvalues are in energy basis. Now what we can do is we can write a vector quantity or a tuple of this form that you see here. So the first is P1 e power minus beta E1, where E1 is coming from the eigenvalues of the Hamiltonian. So these are 0. So this is P1 e power beta 1, then we have P2 e power minus beta 2, P3. Like this we arrange the entire array. First we get this particular array, then we sort this array in the descending order. So we sort the array in the descending order. So suppose P5 that occurs here, P5 e power minus beta E5, if the value of P5 e power minus beta E5, the quantity is highest, we bring it to the front. And then we sort the entire array of V again in the decreasing order. So this is in decreasing order. And now what we can do, now we have to plot X and Y points to get a graph. So what are these points? These points are of this form. We start with 0, 0. And now in X-axis, we choose the maximum value of this. And in Y-axis, we choose this point, this. Now again in X-axis, now we choose the value of this plus the second value. That is this plus this. And in Y-axis also, we sum of the first and the second value. Like this we continue, like in the third case we choose the first three values and first three values of probabilities, but these values have been arranged in descending order. So once we have done that, we will get, let's not look into this part, we will get a curve of this kind. So we will get a curve of this kind such that the final value will be always of this form, the partition function z, 1, because summation of all probabilities will be 1. So the final point will be this, and the initial point is always 0, 0, and this point is z, 1. Now once we have done that, for every state we can understand which state can go to which state. Like this state rho has this curve, it can go below, so transition from rho to sigma is possible. Transition from rho to tau beta, which is the Gibbs state. The Gibbs state is just a straight line joining these 2 points, that is 0, 0 and z1. Because of the very definition of Gibbs state, that it is e power minus beta Hamiltonian divided by trace of e power minus beta Hamiltonian. Now this curve, so rho can transit to this state, rho can transit to this state. Sigma cannot transit to this state because it is above sigma. But sigma can go to Gibbs state. We will observe that whatever the curves be, they will remain above the Gibbs state, and hence any state can make a transition to the Gibbs state, but Gibbs state cannot make a transition. So the Gibbs state cannot go to any other state under this thermal transformation. So we need an external working system or an external working bit or bit storage device or work storage device to make such a transition from Gibbs state to other state. So you see, this is the characterization which characterizes the thermal operations. But now this characterization is very different from the ordinary third law of thermodynamics, which says that such a transition is only possible when the free energy, change in the free energy is less than equal to 0. This is the law of thermodynamics in systems which are thermalized or which are associated with a bath. But actually the thermo-majorization property, we will see in the next video, it is actually much more stronger statement. It is a much more stronger statement than the fact that just the free energy needs to be reduced. It turns out that the thermo-majorization statement requires that an infinite number of free energies, which will be the free Rayleigh entropies, they needs to be reduced simultaneously to make an exact transformation. However, we will also see that for an exact transformation, such an infinite equations is necessary. But if we talk about a finite, like a transformation that does not land us to the final state exactly, but rather a transformation that takes us to some sort of a near state, such that rho tilde plus delta gives us the final state. Such transformations can only be satisfied by a weaker version, which means only one of the free energy, that is the Shannon free energy, needs to be reduced. So that's all for this video. In this video, we laid down the thermodynamics foundations as resource theoretic perspective. So that's all.